All right, so here's another example, and I'm going to find the Nash equilibrium in pure strategies and mixed strategy Nash equilibrium. In the long way, I'm going to find the expected payoffs, I'm going to calculate the best response functions, and then draw them and find the point of intersections. All right, so the first thing first, the easiest part. Well, what are the Nash equilibrium in pure strategies? Let's draw the best responses, the underline the payoffs. So if it happens that player one plays U, what would be the best response or regret-free strategy for player two? Is it, by the way, there are two players, each player has two actions, UD for player one, LR for player two, okay? And here's the payoffs. So the best response would be left because 2 is higher than 1. If player 1 happens to play D, however, the best response would have been R because 4 is higher than 2. All right, so for player 1, given that player 2 plays left, the best response would have been U. And if player 2 was playing right, the best response would be both U and D. All right, the both numbers are underlined and that occurs twice, not here, all right? So therefore there are two Nash equilibria. Equilibria is the plural of equilibrium, and these are UL and DR, corresponding payoffs 4, 2, and 2, 4, okay? So these are two Nash equilibria in pure strategies. Well, what about the mixed strategies? Well, in the mixed strategies, remember, we extend to the PQ business. So player one, let's suppose he plays up or U with P probability. Therefore, D with 1 minus P probability. Player two plays left with Q probability and R with 1 minus Q probability. All right, and hence we calculate the expected payoffs. All right, so the expected payoff of player one, if he chooses U, given that his opponent 2 is playing left with Q probability, what is this expected payoff? So if player 1 is playing U, it means he ensures that this is where the payoffs will be. It's either 4 or 2. He's going to get 4 only if player 2 plays left, which happens with Q probability. So therefore, he's going to get 4 payoff with Q probability, and with the remaining probability, 1 minus Q, he's going to get 2. So just sum them up. You're going to have 4Q minus 2Q, so it's 2Q plus 2. Well, what about his expected payoff if he chooses D instead? Again, given that, so here's the intuition. These players get together in separate rooms. They simultaneously choose a number. Player 1 chooses some P in between 0, 1, and player 2 chooses some Q in between 0, 1. And they write those P's and Q's in a piece of paper. I mean, player 1 writes his P and player 2 writes his Q, and they submit it to the moderator, and the moderator says, okay, the game is over, the P is this and the Q is this, do you regret? And we are trying to find the value of P and Q where they don't regret, okay? That's sort of the intuition of finding mixed strategy Nash equilibria. So if the second player happens to play D, well, what would be his expected payoff? Well, it's either 1, which occurs only if player 2 plays left. So therefore, he's going to get 1 with Q probability and 2 with 1 minus Q probability. So it's going to be 2 minus 2Q, but there's Q, so it's going to be 2 minus Q. So these are the expected payoffs of player 1. Well, let's also calculate the expected payoffs of player 2. So given that this first guy is playing U with P probability, what is expected payoff of player 2 if he happens to play left? So he's going to get either 2 or 2. So regardless of P, it is 2, right? I mean, 2 times P plus 2 times 1 minus P, regardless of the value of P, is just 2, okay? And then expected payoff of the second guy, if he happens to choose right instead, what would be that? Well, he's going to get either 1 or 4, but he's going to get 4 only if player 1 chooses D, which occurs with 1 minus P probability. So with 1 minus P probability, player 2 is going to get 4. With the remaining probability, I mean P, he's going to get 1. So therefore, this is 4 minus 3P. Okay, so these are the expected payoffs. Well, I'm going to calculate the best responses. I'm going to start with player 1 first. Well, the player 1's expected payoffs is, well, there are 3 cases. 2Q plus 2 is greater than 2 minus Q, or 2Q plus 2 is less than 2 minus Q, or they're equal, right? So, if the 2Q plus 2 is greater than 2 minus Q, which is the first case, it means U is more profitable than D. So you should definitely play U, all right? Again, if this payoff is higher than the second one, playing U is definitely more profitable than playing this D. So you should not play D with some positive P. So you should basically play only U, which means you should play U or choose P equals 1. All right? So your best response is P equals 1 is optimal. Well, if the opposite is holding, P equals 0 should be optimal. All right? I mean, intuitively, if D is higher, giving you higher payoff than U, you should basically play D with probability 1. To make 1 minus P equal 1, P must be 0. So, and here, you're indifferent between up and down, and so any P in between 0 and 1 is optimal. Okay? There will always be, so whenever you have equality, so any P is going to be optimal. All right, so when is this true? Let's solve this inequality. So send minus Q here, it's going to be 3Q, and this is going to be 0. So, oops, Q is greater than 0. So whenever Q is greater than 0, P equals 1 is optimal. Good. What about this? Well, 3Q less than 0, so Q is less than 0. Well, this will never happen, by the way. All right, so this will never happen. Never happens. Why is that? Well, the Q and P, these are probabilities. They are at least 0, at most 1. All right? Well, what about this? Well, this is equal to 0. So when Q is exactly equal to 0, right? I mean, 3Q equals 0, and hence Q equals 0. So whenever Q is equal to 0, these two things are the same, and hence any P is optimal. All right, unintentionally, I picked this number because I made up those numbers, but I think that's a complicated problem, which I liked. So let's draw the best response function, all right? So here is the best response function for player 1. So P on the horizontal axis, Q on the vertical axis. There's no reason why I put P on the horizontal and Q on the vertical. It's just convention. All right, so the strategies are on this square. My squares always look like a rectangle, sorry. But these are just 0, 1, 0, 1. So here, the Q equals 0 is a threshold. And Q equals 0 is this, Q equals 0. So whenever Q is strictly higher than 0, all right, so for all those Q values, the P must be equal to 1. So P must be equal to 1. Okay, so if, for example, P equals 50, corresponding P is 1. Whenever Q is equal to 0.9, corresponding P, the optimal P is 1. All right, so P is always 1. Whenever Q is exactly equal to 0, any P in between 0 and 1 is optimal. So I have this weird step function, all right? So those step functions are not necessarily be step function. I mean, like perfectly step. I don't know how to call it. But this is what the step function will, or the BR1, the best response function for player 1. All right, so it goes all the way horizontally, and then, oops, a straight line. So that's the best response function for player 1. Now, the best response function for player 2. Player 2. All right, so there are three scenarios. Either 2 is greater than 4 minus 3p, or 2 is less than 4 minus 3p. That depends on the value of p. Or the third is 2 equals 4 minus 3p, right? So when this is true, it means for player 2, left is a more profitable strategy than R. So if you play R, you're going to regret. You should play L without any uncertainty, meaning you should be choosing Q equals 1. All right, so Q equals 1 is optimal. If the reverse of this inequality holds, that means Q equals 0 is optimal. I mean, sort of the reverse of Q equals 1 is Q equals 0. And whenever you're indifferent to, any Q between 0 and 1 is optimal. All right? The question is, when are those inequalities hold? Well, send 3p to the left-hand side, it becomes plus greater than 2. So as long as p is greater than 2/3, Q equals 1 is optimal. So if I reverse the inequality, I should reverse this inequality as well. So whenever p is less than 2/3, Q equals 0 is optimal. And if p is exactly equal to 2/3, well, any Q is optimal. All right. So let's draw so this is the best response function for player 2. So let's draw this step function. And here a cutoff is 2/3. 2/3 is, I mean, well, okay, so let's say this is Q, this is P, I'm sorry. P equals 2/3, so something around here. P equals 2/3. All right, so what happens is when P is exactly equal to 2/3, any Q is a best response. Oops, that's supposed to be a straight line. So any Q between 0 and 1, again, this is a straight line, is the best response. When P is greater than 2/3, so when P takes the values here, the optimal Q is 1. All right, so the optimal Q is 1. And then when P is less than 2/3, the optimal Q is 0. Okay, so that is a step function. That's the BR2, the best response function of player 2. So here, remember the mix, so that's it. I calculated the expected payoff of each player. I calculated the best response functions, and then I drove the best response functions. Now, I need to find the intersection points of these best response functions. Because when two best response functions corresponds, best response, or sometimes some textbooks call it best reply function, best response functions. So when best response functions intersect, it means at those points, everybody is choosing optimally, so nobody will regret. All right? Hence, the point of intersections will give us a Nash equilibrium. Here, as you can see, there are many points of intersection, one of which is this point, where P is 1, Q is 1. And P is 1, Q is 1 corresponds to UL, which is one of the Nash. This corresponds to UL. So, in conclusion, every pure strategy Nash equilibrium is also mixed strategy Nash equilibrium. All right? Well, another intersection point is Q equals 0, P equals 0. And this corresponds to, when P is 0, it means 1 minus P is 1. dr, and when Q is 0, it means R is 1. So R is played with probability 1. So dr is the other Nash. So this corresponds to dr. So these were the two Nash, pure strategy Nash. However, as you see, all those points are intersecting for those two best responses. So there are infinitely many mixed strategy Nash equilibrium, one of which is P equals 2/3. So in fact, P equals less than or equals 2/3 and Q equals 0 is a mixed strategy Nash equilibrium of this game. All right? So that means in a mixed strategy, player 2 is not going to play L, but in fact he's going to play R. So player 2 is playing R. This is what Q equals 0 means. And player 1 is randomizing between U and D, but this randomization, that P, will never exceed 2/3. If P, as long as P is less than 2/3, player 2 actually prefers to play right. All right, because in expectation, 4 and 1, the expected payoff of 4 and 1 is going to bring him something higher than 2. But once P equals 2/3, left and right is going to give him exactly the same payoff. And when P exceeds 2/3, well, then the player 2 will actually prefer to play left rather than right. All right? So therefore, we have infinitely many mixed strategy Nash equilibrium. So any P less than 2/3 and Q equals 0 is going to form a mixed strategy Nash equilibrium. Well, in a test, for example, I would certainly say or give you 1 point. All right? For example, here, P equals 1/2, Q equals 1/2, and argue or show that this is not Nash equilibrium. Well, how would you argue that? Well, there are two ways. One, you can just draw this best responses and say, hey, you know what? 1/2 point is somewhere here. I mean, maybe just in the middle. So 1/2. So this is the 1/2 point. It's clearly not on the best response function of any player. And hence, both players will regret from this choice. That's one way of showing it. And then the second way of showing it is the following. Oh, if player 2 happens to play 1/2, all right, so if Q is 1/2, which basically therefore, in which category we fall? Well, we fall into this category, right? So Q is 1/2 means Q is greater than 0, right? Well, in this case, the regret-free strategy for player 1 is choosing P equals 1, but he's choosing 1/2, so he's going to regret. Well, how come? Well, if you calculate the player 1's expected payoff, when he, that's a good point. I know we already exceeded 15 minutes, but let me do this as an exercise. So here's the exercise. What is the expected payoff of player 1 if this is the strategy? All right, so P is equal to 1/2, Q equals 1/2. What is the expected payoff of player 1, given that he plays P 1/2 and the other guy plays Q 1/2? What is that equal to? Okay. So the player 1's expected payoff, what happens is that if he plays U, he's going to get this. When Q is equal to 1/2, this is going to be equal to 2 times 1/2, so 1 plus 2, 3. And if he plays D, if player 1 plays D, his expected payoff will be 2 minus 1/2, which is 3/2. Okay? So what happens is the P is 1/2, meaning he's playing U with 1/2 probability. And he is playing D with the remaining probability, 1/2. So if he plays U, he's going to get payoff of 3. If he plays D, he's going to get payoff of 3/2. With 1/2 probability, he's going to get, therefore, 3. And with 1/2 probability, he's going to get 3/2. So I just multiply the probability with the payoff. This is what expected payoff is. So it's 3/4. And hence, if you add them up, this is going to be 6/4. So 6 plus 3, 9/4. Okay. Well, the question is, well, is this the best response? Well, by the way, 9 over 4 is, well, 9 over 4, 1, no, 2 point, so it's 2, so if it was 8, it would be 2, so it is 2.25, I believe. Yes. So, however, if he plays only U, he would have gotten 3. All right, so this is why his best response is P equals 1. I mean, play U for sure. But you force him to mix between U and D. And so by playing U, he would guarantee payoff 3. But because he's randomizing between U and D, his payoff will actually go below 3, which is 2.25. And therefore, he's going to regret of his choice because his optimal thing is to play U with probability 1. And because of this, so at least one player has incentive, not incentive, he's going to regret of his choice. So therefore, this cannot be Nash. All right? Again, conclusion is easier once you draw the best responses, but you can conclude the same thing or sort of argue that it's not Nash without drawing it, but you have to use or rely on the best responses because the best responses basically a way to sort of solve the player's no regret strategies, the best response strategies. Okay? Yeah, that was a little long, but I hope it was clear. All right?